Hi everybody. This is our lecture on section 4.2. It's on the null space and column space of a matrix, as well as kernel and range of linear transformations. Okay, let A be an R by C matrix. R rows, C columns. One moment. Definition: the null space of A which is denoted by just this null A, like that, is the set of all x such that A times x equals 0. So, we've looked at this type of equation many times before, right? A matrix equation, A times x equal to 0, which is always consistent and either has a single or many solutions. Okay, so notice that null space of A is a vector subspace, just subspace, of vector space RC, number of columns, right? Because you're multiplying x by A, multiplying x on the right of A, right? So the number of entries in x is the number of columns in A, so that you can do this multiplication of a row of A times the column x, right? Is a subspace of vector space RC. Furthermore, if A has P pivots, then null space of A is a span of, well, how many? So, of how many vectors? Of how many vectors? So what you do is you reduce A into reduced row echelon form, right? The non-pivot columns correspond to the free variables, right? And the pivot columns do not, right? So it's those non-pivot columns that give you the free variables, right? And those number of free variables is the number of linearly independent vectors. So we've gone over this before, but we'll go over another example right now. So it's the number of columns minus the number of pivots. It's a span of C minus P linearly independent vectors. So for example, all right, so express the null space of A as a span of linearly independent vectors with A equal to 1, 5, negative 4, negative 3, 1, 0, 1, negative 2, 1, 0, and 0, 0, 2, negative 4, 2. So there's A, right? So in order to look at the solutions of A times X equal to 0, right? We need to, that's the null space. We need to reduce A to reduced row echelon form. Now this was the question in the exam that folks had trouble with. So please, let's make sure we know how to do this. This is important. So first I'm going to subtract row 3 from row 2 from row 3 twice. 0, 0, 1, negative 2, 1, and then this gives me 0, 0, 0. Right, and then I'm going to subtract this, or add this row 2 to row 1 4 times. 1, 5, 0, negative 8 minus 3 is negative 11, and 1 plus 4 is 5. Alright, so now we're in reduced row echelon form. The pivots are right here. And the pivot, the column for the pivot, has one non-zero entry. That's reduced row echelon form. Right, so the free variables are the non-pivots, x2, x4, x5. Right, and then x3, which is non-pivot, is 2x4 minus x5, and x1 is equal to minus 5x5 plus 11x4 minus 5x2. All right, so that's the description of our variables, but we're not done yet. Okay, and what we want, right, is to express the null space of A as a span of linearly independent vectors. Okay, this is not described as vectors yet, right? I mean, these are the solutions, right? These guys are free, and then x1 looks like this in terms of the free variables, x3 looks like that. But we want to write it as a span. So we do like that. So we have minus, so let's see, minus 5x2 plus 11x4 minus 5x5, and then x2 is just x2 because it's free. x3 is 2x4 minus x5. x4 is x4, x5 is x5. Okay, so what do we have? We have x2 times the vector minus 5, 1, 0, 0, 0. Plus x4 times the vector 11, 0, 2, 1, 0. 11, 0, 2, 1, 0. Plus x5 times the vector minus 5, 0, minus 1, 0, 1. So there it is. So the null space of A is the span of these three vectors. And those vectors are linearly independent because the matrix with those vectors as columns well, these three columns has three pivots, as I'll show you in just a second. Alright, so it's the span of these three vectors, and if you imagine the matrix consisting of these three columns, if you imagine that matrix, you see you have a pivot here, here, and here, which is a pivot in every column. So that means those vectors are linearly independent, and the fact that they always come out that way is because we reduced the matrix A to reduced row echelon form. All right, so these three vectors are linearly independent because the column, the matrix with these three columns, has three pivots. Right? It's just automatically turns out to be that way. All right, please, you guys, this just basic thing about the null space of matrix, the solution of a system of linear equations, and writing the solution as a span like this. I mean, this is like so much of the course is just based on this. So could we please understand how this process works? Okay. All right. Yeah, and yeah, the number of columns, right? The number of linearly independent vectors that you get is C minus P, where P is the number of pivots, because those guys correspond, because the free variables correspond to the non-pivot columns. So C minus P. All right, that'll be important later. All right, so that's null space. Column space, I mean, it's something we know already. We're just putting sort of new terminology around it. So, given an R by C matrix A, the column space of A, which is denoted by call A, is, well, it's the set of all vectors B such that A times X is equal to B for some X. All right, in other words, all right, if A is this matrix with column vectors V1 to Vc, then the column space of A is just the span of V1 to Vc. And later on, we will have, so this is a span of vectors, right? It's just a span of vectors, but those vectors aren't linearly independent. So in some sense, this is an inefficient description. But we didn't quite cover the technique yet that will allow us to get a more efficient description. But anyway, so what do we see so far? So far, that one, the column space of A is a subspace of vector space RC. No, RR, sorry. RR, the number of rows, because each column has R rows. So that's a subspace of RR. It's a subspace because it's a span, and spans are always subspaces. Okay, later, we don't have it yet, that the column space of A can be expressed as a span of P linearly independent vectors where P is the number of pivots in A. So P is the number of pivots, and that's the number of linearly independent vectors for the column space of A. Whereas the number of columns minus the number of pivots is the number of linearly independent vectors for the null space of A. So those two numbers, P plus C minus P, is just the number of columns, which is kind of neat. Now, that'll be important later. All right. So here's an example that uses this idea. So consider the set of all vectors of the form b minus 5t, 2b, 4d, d, such that b and d are real numbers. Any real numbers. Show that, let's call this something, let's call it, show that W is the column space of a matrix, and therefore is a subspace of vector space. Well, which vector space? We have 4 entries in the column, so it's R4. Okay? All right, well, we can just look at this. Right, and write this as follows. It is B times 1, 2, 0, 0 plus D times the vector minus 5, 0, 4, 1. Right, so this is equal to the matrix 1 minus 5, 2, 0, 0, 4, 0, 1 times the vector BD. All right, so W is the column space of this matrix here. Of this matrix. Okay. Similar example. Show that W is not a vector space by showing that one of the vector space axioms fail for some particular vectors. All right, well, here, this is very similar to the W. The only thing is I put that plus 1 there, right? So here, let's just copy this over. All right, I've got this plus 1 here, right? So this is equal to b times this plus d times that plus this particular vector 0, 0, 1, 0. So let me change that to just minus d, make that a little easier. Well, why is this not a vector space? Well, a vector space always has to have the 0 vector. Okay, so therefore W is not a vector space because it doesn't. Is not in W. Why? If we were to get 0, 0, 0 in W, so to have the third row equal to 0, right, must have 1 minus d equal to 0, so d is equal to 1. But then you got to have b minus 5d is 0, but d is already 1, so b is equal to 5. But then, well, once you have d equal to 1, sorry, I don't need to do all that, must have that 1 minus d is equal to 0, so d is equal to 1. But then the fourth row is not 0. Right, so this one fails to be a vector space. Unless you can express it as the column space of a matrix, something like this, it's going to fail to be a vector space, often because it just doesn't have the 0 vector in it. Okay, or it's not closed under addition. Yeah, probably those two things. It's not closed under addition, or it fails to be fails to have the 0 vector in it. All right. So the final topic here in this section is just to basically cast these ideas in terms of linear transformations. Okay. Given a linear transformation T, the kernel of T is the set of all vectors x such that T times x is 0. So notice that if Tx has matrix A, then the kernel of T is just the null space of A. Not that you know, sometimes for infinite dimensional vector spaces, you don't have this sort of well-defined idea of a matrix for a linear transformation. They have a couple nice examples in the section, at the end of the section. Where'd it go? Yeah, example 8 and example 9 on page 207, where they talk about the differentiation operator. There, you know, the dimension of that vector space, you know, this vector space of all functions is infinite. So you don't really have a matrix. So this idea of a kernel really is different than the null space of A. But we don't really deal with that in this course. That's something more for a graduate level course in mathematics. So really the kernel of a linear transformation is just the same as the null space of a matrix. Because we're only dealing with finite dimensional vector spaces. And then the other idea is that the range of a linear transformation T is the set of all B such that T of X is equal to B for some X in the domain. Okay, and this is just the column space of the matrix that goes with linear transformation. So when T of X is equal to AX for some matrix A, the range of T is just the column space of A. Okay, so there's a terminology in terms of linear transformations for null space and column space. Okay, and they're important ideas. So we take this time to go over them carefully. Okay, that is the lecture for section 4.2.